Hi everybody who is watching this fantastic video. I'm very happy to have you, and I would like to welcome you, and I have a good news for you. So get in touch and stay tuned into these YouTube channels and into these programs where that we are going to deliver some very important information for you. My name is Olenjolai TAYAI. Simply just call me Sir Olenjolai from Tanzania, eastern of the African country. I'm very happy to have you today, and I would like just to spend a few minutes to welcome you and give you a few informations if it's your first time. But if it's your second time or third times, or maybe it's your nth time, then it's wonderfully like just to remind you every time so that you may stay focused and stay connected, and actually that you have the same directions like the direction that we are taking in. We'd like to take this opportunity to welcome all our international and the national viewers, whether students or guardians or parents or sponsorships or sponsors or teachers or trainers or tutorial assistants or professors or lecturers. We'd like to welcome you into our online undergraduate Polytechnic Institute of Tanzania in square bracket OLENJOLAIM. Simultaneously, we have one of the universal and even in universal and global channels that's called YouTube channels, which is called the Online Undergrad. These are abbreviations of undergraduate POLYINSTIT of Tanzania in square bracket OLENJOLAIM. Well, so the next question that comes in your mind, what are we doing in Tanzania in Online Undergraduate Polytechnic Institute of Tanzania in square bracket OLENJOLAIM? Well, that's a very fantastic question, and I would like just to spend a minute to answer your questions. However, that we have a video which are titled as Lecture 00, the General Introductions of the Calculus, which give you too much information concerning about your questions of the visions pursued by Online Undergraduate Polytechnic Institute of Tanzania in square bracket OLENJOLAIM. Well, I have an assignment of teaching, training, incubating, mentoring, lead, and even motivating and encouraging some group of students who are pursuing engineering and scientific courses to extract knowledge and wisdom from the formal educations of the year fundamental and the even core courses, and combine that fundamental knowledge, or just combine that knowledge and wisdoms with the knowledge and wisdom that I will teach them also to extract from the Word of God in order to solve real life problems. So our visions simply has 4 parts, which are very important: to extract knowledge and wisdom from the formal or informal education of undergraduate level, and also to extract knowledge and wisdom from the Holy Bible, and then to combine these two knowledge, and the first part, to solve real life problems. When I say about real life problems, we have so many real life problems in our community. We have so many real life problems in our families. We have so many real life problems in our nations, in our countries, in our continents. We have so many real life problems which need engineering and sometimes spiritual solutions. Engineering solutions, spiritual solutions, scientific solutions, mathematical solutions. So there are so many ways that we can solve these real life problems, and every problem is dedicated by God Himself to somebody to solve in order for him to have meaning in life and purpose of living. Okay, so what we are telling you actually might seem like it is difficult to achieve, and even ourselves also, because I'm a product of what I'm teaching you right now, and I'm a product of these visions in my own life. Actually, it has been something impossible for the first time. But I want to tell you that right now, because I took some procedures and follow laws and rules of God Himself, how He has been solving critical problems by using different ways of approach. And hence, I find that it is possible, because now I'm enjoying the fruits of what I'm telling you, that to extract knowledge from the formal and formal education, to combine the knowledge of the Word of God, and then to solve real life problems. So for example, myself, I'm solving a national real life problems on these programs of teaching. Wow. So that is the visions. We have our main objective here is to see our own continuing and even graduate students or teachers or parents or sponsors or scientists or engineers who are different aspects of life. So we are learning to see them, they are solving real life problems, or mathematicians. So we honor all our viewers from different aspects. So we have so many departments in Online Undergraduate Polytechnic Institute of Tanzania. One of the departments is Higher Engineering and Scientific Mathematics, and we are teaching 12 modules or 12 courses in this department, and one of the course or modules is called the calculus. Again, we have in these modules of calculus, according to the NACTE curriculums or NACTE syllabus of Tanzania, it means National Council for Technical Education. So we have 7 chapters, and we are in chapter 5 that called Fourier Series. And then we are in the first subtopic. We are going to learn 6 subtopics in this, 5 subtopics in this topic, which is called Fourier Series of Periodic Functions. And this is lecture 2, titled as Derivations of the Formula of Fourier Coefficients. So this course, it can be covered in first year or second year of study. For instance, at the Dar es Salaam Institute of Technology, where I used to teach this course for 5 or 6 years, this is the first semester course of the first year for undergraduate students. Remember that. In Online Undergraduate Polytechnic Institute of Tanzania, square bracket OLENJOLAIM, we are going to share contents specifically for undergraduate students. In case that you are not an undergraduate student, we have a good news. Just click the buttons of show more, where that we call it in YouTube channels as well descriptions. It means go to the descriptions of this video. You will see links of our other online institutions for ordinary diploma, and also 4 online schools, 2 for the spiritual knowledge, and also 2 for the and another school for the ordinary secondary students, and also another school for advanced secondary students. So don't wait and don't hesitate yourself. If you're not an undergraduate student, then you can go into our other platforms so that you can get what you are expecting to get in Tanzania or online, and actually at any time and anywhere. So another thing that I'd like to share with you right now is actually that in case you feel from your hearts that you want to offer God your free willings offering, your Thanksgiving offering, or your free willings seed offering, or your free willings just the covenant offering, or your free willings vow offering, any kinds of the offering that maybe you wish from your heart or feel from your heart you want to offer God through Online Undergraduate Polytechnic Institute of Tanzania, then you are warmly welcome. And then your free willing Thanksgiving will be received in order to support the running cost for these actual national and international programs to be continuing providing essential content. So let us go now to today's session, so today's class. Okay, so I would like to link this lecture 2 with quick review, with lecture 1. Okay, quick review of quick review of lecture 1 of Fourier series. Remember also that we have so many resources and so many videos, teaching and training videos about higher engineering scientific mathematics in our channel. So in lecture 1, basically, we define first of all calculus, because Fourier series is just no. Did we define calculus? No. So we define the terms. First of all, it means that I mentioned topics of 14 topics, 7 topics. I mentioned the 7 topics of 14 of calculus. Okay, and then I mentioned 5 subtopics, which for me I call them topics of 14 of Fourier series. Then in this lecture I defined Fourier series. What I mean of Fourier series? And then we say that this is an infinite series of trigonometrical functions which have different constituents and represent the authority of a periodic function. First of all, a Fourier series is a periodic function. So we discussed about Fourier series, and then we focused on periodic function. And for the function to be a periodic function, we say it should obey the condition of periodicity, which is f of x is equal to x plus, let's say, 2 pi for this case. Okay, that's the condition of periodicity. But if the function is not periodic, we say that it is not equal to f of x plus 2 pi. So then we left the homework for you. I believe that and else we left the homework. That's all about homework 1. Okay, homework 1, we say that show whether the following functions are Fourier, are periodic functions or not, right? The first function we gave you is tan of theta. The answer is this is periodic function. Then the second function is what? So you can show, okay, tan of theta. The second function is cos theta. Also the answer, this is periodic function. And also we have the third function, which was cosec of theta, because these are reciprocal of cosec is the reciprocal of cosine, cosec is the reciprocal of sine. Also this is periodic function. That's the answer. Okay, because you have to state whether they are periodic function or non-periodic function. And then the first example, say y is equal to x squared. I think that's 3x squared if I'm not mistaken. Also this is non-periodic function. So that's the correction for what? This is the quick correction for what? For homework 1. So let us go to today's business. Are you ready for that? Tell me in the comment section that you're enjoying these contents globally and even whether nationally or internationally, from which institutions or college or university, from which country, from which region. If you are enjoying these contents from any of the 31 regions of Tanzania, tell us in the comment section. And also tell us from which country if you are enjoying these contents internationally, right? Don't forget to tell us in the comment section, because we have a vision to see thousands of undergraduate students get help on this stuff. Okay, so we are dealing today with, I want to teach you about derivations of formula of the Fourier coefficients. But before I teach about derivations of the formulas of Fourier coefficient, I would like to spend a few minutes first of all to give you the Fourier series, because the general formula of Fourier series. Because the general formula of Fourier series is one of the interesting formula that will get all the of its coefficients. So, ladies and gentlemen, let us start with general formula of Fourier series, right? General formula of Fourier series. How we can deal with Fourier series. Okay, so general formula of Fourier series. So we say that the basis of the Fourier series, is that all functions of practical significance which are defined in the interval, of negative pi to pi, can be expressed in terms of a convergent. So this means that its one cycle can be expressed as convergent. Say convergent. I'll teach about convergent series or convergent series. Okay, convergent trigonometrical series in one of the one of the modules that taught at University of Dodoma called the Calculus 2 trigonometric series. Trigonometric series. Okay, trigonometric series of the form, trigonometric series of cosine and the sine. Okay, so the basis of Fourier series is that all functions of practical significance which are defined in the interval of negative pi to pi can be expressed as a convergent trigonometrical series of cosine and sine, right? So what does this mean? For instance, we say that if you do remember the figure 121, okay, graph of the sine, okay, so we say that suppose this is 1, and this here we have also a range of -1, right? So we say that, for instance, you want to, this is the sketch of sinusoidal function on the positive side, and this is the sketch of the same sinusoidal function, but here we have -pi, here we have -2 pi, here you have -3 pi. Then this is pi, it means 180, this is also 360, this is 3 pi, and this is 4 pi. Right, so you find that from here, this point to this point, we have a completed cycle of 360. So simply we can deal with this function when we can define it from -pi to pi. Or in other books, we can define this function from 0 to 2 pi. Okay, from 0 to 2 pi. But it's better to define that function from -pi to pi because in mathematics, we consider the negative x-axis and positive x-axis, right? So that's what we do in mathematics. So this is the kind of interesting definitions of of a complete cycle. So now, the general formula. So if this is the case now, the general formula of Fourier series is given as. So ladies and gentlemen, after giving you that a little bit introduction to general formula, so let me present you the general formula of Fourier series. The general formula of Fourier series is given as this. Have f of x, this is equal to a naught plus what? Okay, plus, so let me give you the general formula and then I will define the series. Okay, plus summation from n is equal to 1 to infinity. And then here we have an times cosine of nx plus summation from n is equal to 1 to infinity bn, or b subscript of n, then sine of nx. So this is the general formula of Fourier series over the period of what? Over the period 40. So remember that this is for -pi less than or equal to x less than or equal to pi. So that's the general formula. This is the general formula of 40 of Fourier series that you are going to deal in this first subtopic. Wonderful, right? So accept it. There's a way I know how to derive this formula from by combining different concepts of mathematics until we have this formula. But it's beyond of this course. It's beyond of this module. So I'm not going to teach you how we deduce or derive this formula mathematically. But I will teach you how to derive the Fourier coefficient. What are the Fourier coefficients? Fourier coefficients actually are just like the normal coefficients in polynomial function. We talked about polynomial functions, and then polynomial function, we have variables, we have non-negative, we call non-negative integer exponent. We have also coefficients. We have basic operations, whether additions or multiplications or subtractions. So it means that there we have coefficients. So coefficient, simply it's a number. In case of polynomial function, it's a number before the variable. Similarly, in this context of Fourier series, when you say about Fourier coefficient, we mean about a number or a function before the trigonometrical function, right? So for instance, before the trigonometrical functions or its itself. So it can be either a Fourier coefficient which does not contain any what, especially this is just for the only the first term. The first term, usual, if it is there, then you'll find that it does not have, or it extends itself, right? So the trigonometrical function has exponent of 0, because any trigonometrical function, for example, sine power 0, the sine of x power 0, it is 1, and cos of x power 0, it's 1, right? So that is, but in case of other Fourier coefficient, the second and third Fourier coefficient, these will be written or will be preceding trigonometrical function. So an will be preceding the cosine of nx, and bn will be preceding the sine of 40 of nx. So that is the general formula of 40 of Fourier series, and you have to keep it in your mind, because we are going to use in this lecture 2, in lecture 3, in lecture 4, in lecture 5, in lecture 6. So you have to keep it in your mind. So that is the general formula, right? So then we say that in generally also, it means that we say the general Fourier series is, so the general Fourier series is what is given as this: f of x, this is equal to a naught plus a1 cos of x plus a2 cos of twice x plus a3 cos of 3x plus. Okay, I believe that you enjoyed the beauty of higher engineering mathematics. And if you're scientisting, I believe that you enjoyed the beauty of higher scientific mathematics, right? So I believe that you enjoyed, because these are actual. So plus, then we have what? A subscript of 4, this is Fourier coefficient, and then we have cosine of 4x, then plus dash dash dash, right? Again, we add with what? Plus, okay? So you say plus, do we have any terms there now? Just to say plus, then we start writing the b1 sine of what? This is when n is equal to 1. So sine of x plus when n is equal to 2, it will give us b2. Then we have sine of twice x. When n is equal to 3, it will give us b3, then sine of 3x. And then when n is equal to what? To 4, then it will give us b4, sine of 4x, and then plus dash 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 dash. Okay. So that is the general Fourier series. So this is what you have to expect. This is the general formula in sigma notation. So this is the shorthand of writing Fourier series, right? Remember, listen carefully. This is the shorthand of writing Fourier series, right? But in many cases, when we're solving problems, we will never end at this stage. We'll be finding the Fourier coefficient. Our business is to find the Fourier coefficient, an and bn, right? After we get them, then we have to substitute them into the general Fourier series formula. And when we substitute them, you know what are we going to do then? We know that our sigma notation is from n is equal to 1 to infinity. So we substitute when n is equal to 1, a1, then we have cos of 1. When n is equal to 2, a2, cos of 2x. When n is equal to 3, a3, cos of 3x. When n is equal to 4, a4, cos of 4x, right? And then similarly to this, secondly, the third term, right, or the third sigma notation, so the second sigma notation. When n is equal to 1, we have b1 sine of x. When n is equal to 2, we have b2 sine of 2x. When n is equal to 3, we have b3 sine of 3x. When n is equal to 4, we have b4 sine of 4x, right? So plus dash 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 dash, because we say that until we have the infinite. So this is infinite series. So this is what you have to expect, right? So remember that. But we have a note before we take you into the Fourier coefficient. And this is the note. We say that Fourier series has a great advantage this Fourier series has a great advantage compared to other series. We have taught you about other series. Do you remember those other series? We have talked about Maclaurin series. We have talked about the Taylor series. So we have taught you so many different types of the series. We have talked about binomial series, right? So then, you know what Fourier did actually during his research of publications of his PhD thesis, right, or research. Then he compared his own series with also other series. So listen, the great advantage of Fourier series that every engineer has to know, and every scientist has to know, and every mathematician has to know. Are you ready for that? Let us go inside. A great advantage of Fourier series. A great advantage of Fourier series over other series. Such as Taylor series, Maclaurin series, is okay. The great advantage of Fourier series over other series such as Taylor series, Maclaurin series is it can be used or applied, okay, to function. This is applicable to function which are continuous and the non-continuous or discontinuous function. Discontinuous, the function which are continuous and what is discontinuous, as well as continuous functions, okay? Okay. So you see, Taylor's series, Maclaurin series, this series will be applicable to the functions which are only continuous, right? While Fourier series has a great advantage that can be applicable to the functions which are continuous and also non-continuous. So you see the advantage of Fourier series. Every scientist, every mathematician, every engineer has to understand and have to know. So that's why that we have to study intensively about Fourier series, and kids be during the modeling and during the actual advancements of the curriculum. So during the curriculum review of calculus, then they say we have to give this series a special honor to study it as a topic, right? So remember that we are going to deal with continuous function and the discontinuous function, and how we can find a Fourier series. Stay tuned. Okay, so the next part of this lecture, ladies and gentlemen, is I would like to take you now into the part of the title of this of the lecture 2, and let us focus onto the Fourier coefficients. So you say that the general formula, so let us focus on Fourier coefficients, which will be fine, okay, coefficients. Because remember that I have to teach, I'm still building the foundations of Fourier series. I didn't start yet to teach you about Fourier series. I'm still building the strong foundations that will be there, or that will be helping present and future generation. Fourier coefficients. Okay? What are the Fourier coefficients? What are the Fourier coefficients? So simply that we say that, because that the very important questions we have to ask ourselves. So the question we have in play or on the spot for today's, let's say question 1, I think that this will be question 5. What is Fourier coefficient? What is Fourier coefficient? So you can pause your video and ask yourself that question before. What are Fourier coefficients? What are Fourier coefficients? Okay, what are Fourier coefficients? So I found one definition which can help you and give you the overview of Fourier coefficient. So Fourier coefficient okay, so Fourier coefficient are the coefficients of 40 are the coefficients. So this coefficient may be a functions, okay, are the coefficients of Fourier series, Fourier infinite series. Okay, finite series. That's a simple definition. Fourier coefficient are the coefficients of Fourier infinite series. Okay. So we say that from the general formula of Fourier series, which is f of x, this is equal to a naught plus what? Summation n is equal to 1 to infinite, and then you have what? A n cos of nx plus what? Sigma notation, when n is equal to 1 to infinite, then bn sine of so let us proceed. As well, here I've been teaching you, or I've presented to you about the general Fourier series, which is given as f of x is equal to a naught plus a1 cos of xc plus a2 cos of 2xc plus a3 cos of 3xc and plus a4 cos of 4xc plus dash plus b1 sine of x plus b2 sine of 2xc plus b3 sine of 3xc plus b4 sine of 4x plus dash 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 dash. Not before a great advantage. This is the great advantage because, you know, Fourier has asked himself these questions and even ourselves also as a present and future mathematicians or present and future engineers or present and future statistics. We have to ask ourselves, why do we need Fourier series? What its own advantage? We have learned about Taylor series, we have learned about binomial series, we have learned about Maclaurin series. Why do we need Fourier series in engineering? Well, one of the great advantages that other series such as Taylor series and even Maclaurin series, those are the series for the continuous function. Because remember that in the topic of theory of the limit, I told you about continuous function at a particular point or at a particular interval and this continuous function. So the goodness or the great advantage of Fourier series is we say that the great advantage of Fourier series over other series such as Taylor series, Maclaurin series, is it can be used or applied to functions which are continuous and functions which are discontinuous. You see, its own advantage. So Maclaurins and Taylors cannot be applicable for discontinuous function, but Fourier series, it can be applicable for what? For Fourier series applicable for discontinuous functions, as we are going to discuss, especially the second subtopic or second topic that we call the Fourier series of non-periodic functions. So non-periodic function means this kind of discontinuous function. Then, ladies and gentlemen, let me teach you about Fourier. Ladies and gentlemen, let me teach you about Fourier coefficients. Say Fourier coefficients, right? Fourier coefficient. So Fourier coefficient, what are the Fourier coefficients? That's a very important question that we should ask ourselves as engineers or as mathematicians or as scientists. Fourier coefficients are the coefficients of the Fourier infinity series. These are the coefficients of Fourier coefficient. These are the coefficients of the terms, coefficients of the terms of Fourier series, of the terms of 40 of Fourier series. So these are the coefficients of terms of Fourier series or Fourier infinite series. So Fourier coefficients are the coefficients of terms of Fourier infinite series. From the general formula of the Fourier series like this one, which is f of x is equal to a naught plus sigma notation from n is equal to 1 to infinity, a n cosine of nx plus sigma notations or summations from n is equal to 1, summations of bn sin nx from n is equal to 1 to infinity. Okay, so from this general formula of Fourier series, which is f of x is equal to a naught plus summation of a n cos of nx from n is equal to 1 to infinity plus summations of bn sin of nx from n is equal to 1 to infinity. The Fourier coefficients are a naught, a n, and bn. So these are the Fourier coefficients: a naught, a n, and bn. And these are the three coefficients that Fourier coefficient I have to teach you how to derive its formulas. As the title of lecture 2, Derivations of Formula of Fourier Coefficients. So ladies and gentlemen, right now, for the remaining part of this lecture, we are going to deal on how we can derive the formula for a naught and a n and bn. And possibly, for those serious students, I would like just to challenge you. The way we are going to find or to deduce the formula for the bn is similar to the way that we are going to deduce for an. So once I teach you about an, then because here we are going to just multiply with the cosine integral of the cosine function, while here we have to multiply with the integral of the sine function. Same intervals means same lower interval and upper interval. So you have to be careful. So you have to deal with this with this Fourier coefficient. But because we need these formulas to assist us or to help us in comprehensions or in comprehensions of lecture 3 and lecture 4. So I'm going to derive all the three so that in the next lecture we have to recall them and solve, because you know that we are going to do kind of more algebraic work, meaning that when we be solving a questions of Fourier series of Fourier series, whether it is step functions or it's just a normal polynomial functions or trigonometrical function, really want to tell you that we are going to follow so many steps. So that's why that they want to clearly teach you and build the foundations of these formulas before we are going to use them effectively. Okay, so now let us say the derivation. Let me teach you about derivation. If you have any question, ladies and gentlemen of undergraduate students, don't hesitate yourself to ask in the comment section. And then I'll try my level best to answer your questions. And not only me, even also other teachers around the world and also other students around the world can answer your questions because we like questions from our students. Derivation of Fourier coefficient, Fourier coefficient, Fourier coefficient of A naught, or Fourier coefficient of A naught. Okay. Well, so we say that we'll be following some steps. It means that we have to use Fourier, the general formula of Fourier series to derive the formula of A naught. Right? In some of the books, you can use the capital A naught. That's not a deal. So we'll be following some steps. The first step, we say that recall Fourier, general formula of Fourier series. So general formula of Fourier series is f of x is equal to A naught plus summation of an cosine of nx plus, so from n is equal to 1 to infinity, and then plus summation from n is equal to 2, no, n is equal to 1, excuse me, to infinity, bn sine of nx. So this is our first equation. Okay, first equation. Okay. So then we say that, okay, fine, that's a great deal. Let's now think on how we can simplify that for this general form of Fourier series until we get a coefficient A naught. Okay. So we go for the second step, ladies and gentlemen. Second step, we say that multiply equation 1 by integral from negative pi to pi dx to both sides. Multiply equation 1, multiply to both sides of equation 1. So if you multiply with this one on the left hand side, we are going to have integral from negative pi to pi, which is a complete cycle, as I told you, f of x dx. This is equal also to the integral from negative pi to pi. Here, I want to tell you, ladies and gentlemen, Fourier series employs different techniques of integrations. So we taught you integrations during your ordinary education, so during your advanced education. Yes, you have to recall all of those concepts here because we are going to integrate more than you think, right? So then we say that here we have A naught dx plus what? Plus integral. So then we have a sigma notation right now. So the way that we are writing sigma notations and integral sign, we have to write the sigma notation first from n is equal to 1 to infinity. And then inside of sigma notation, we have our integral from negative pi to pi. Then we have an Then you have cosine of nx dx plus sigma notation, ladies and gentlemen, n is equal to 1 to infinity. Then you have what? Bn, sine of what? Sine of nx. But here we have integral, excuse me. So first of all, we have integral from negative pi to pi. Then we have Bn sine of nx dx. So this is our present formula, right? So you have to think. We have nothing to do on this part because it is just a function. We don't know which functions are we going to be given in the question. Even on this side, we can solve this because we know that it's a constant. It's integral of constant a naught with respect to dx. And then we can predict it. We can know also the response for this part. And then we can know the response on this part, right? Because we're integrating just the Bn sine of nx and an cos of nx. Okay? So you have nothing to do with the stuff of what? So you have nothing to do with, means these are, we call them orthogonal function, if I'm not mistaken, yeah. Orthogonal function. So you go for the steady state. The steady state, we say that recall the concept of integrating, orthogonal, say orthogonal perpendicular, at the means of orthogonal. Orthogonal function over negative pi to pi. So orthogonal functions of negative pi to pi. So what does it mean? This orthogonal function, we say that we can just take one of them and deal with it. Why we call it as orthogonal functions of a particular function. For instance, that we want to integrate negative pi to pi, forget about the coefficient an, then you have cosine of nx dx. So if you integrate this, then we'll get to the sine of nx over n. Then the intervals is from negative pi to pi, right? And then we say that next, what will happen is, so next we say that we have 1 over n, then substitute the limit, we have what is sine of n pi, then minus what? Sine of negative n pi. So because sine it's an even, it's odd function, which I'll teach you soon, then this will be positive and this will be positive. Right? Okay, because that's the formula for the xn. So if it will be positive, no, minus, so negative, so it will make this what? So it will make what? It will make, okay, yeah, it is true. So it will make, this is still negative. Still negative for the different aspects. So simply you find that for orthogonal function, if you integrate it from negative pi to pi, of course n in the x dx, because you remember that an and this an and bn, those are just a coefficient. You can take them out of the integral sign, and then we'll see what happens around. So for orthogonal function, so simply for orthogonal, so bear this in your mind. For orthogonal function, we say that integral from negative pi to pi of cosine of nx dx, this will be equal to integral from negative pi to pi of sine of nx or x, let's say, okay, x dx, and this is equal to 0. So integral of these two functions will give us So if that's the case, if we go back to our formula, so you have for integral from negative pi to pi, then you have f of x dx. This is integral from negative pi to pi. Then we have what? We have a naught dx plus what? So you have again here, you can say that you have summation from n is equal to 1 to infinity. And hence you have an. So integral from negative pi to pi, then you have what? Cos of nx dx plus what? Plus summation from n is equal to 1 to infinity. Then you have bn, integral from negative pi to pi. Then you have sine of nx dx. Right? So this is a orthogonal integral function and orthogonal integral function. So if you integrate this, we get 0, integrate this one, you get 0. Okay? So suppose that this is the question what? Question 2. This is question 3. So suppose that this is question 3. This is question 3. And this one is equation 2. Okay? Okay, so you say that the first state right now, substitute values of equation 3 into equation 2. So then we have integral from negative pi to pi of what? F of x dx. This is equal to what? That is equal to negative pi to pi a naught dx plus 0 plus 0. Right? Remember that you are deriving the general formula of Fourier coefficient a subscript of 0 or a naught. So if that's the case, then we say that we can just rewrite this in this format. We didn't change anything. This is a naught dx is equal to integral from negative pi to pi, and then you have f of x dx. Right? So then we take a naught out of the bracket. We have integral from negative pi to pi dx. This is equal to integral from negative pi to pi of f of x dx. So remember that this is x power 0, which is equal to x naught. So a naught, if you integrate this one by using the power rule, it can be 0 plus 1. Okay, so you have x and then still you have 0 plus 1 from negative pi to pi. So this is equal to integral from negative pi to pi, then f of x dx. So here we have a naught, and then you have what? So we have x power 1 over 1. So it means that in variable of x we have pi minus negative pi. This will make integral from negative pi to pi f of x dx. So then this will make a naught. Pi minus negative pi, this makes 2 pi, is equal to integral from negative pi to pi of f of x dx. Okay, I believe you enjoy the beauty of higher engineering mathematics and higher scientific mathematics. Right? Good. So here we have 2 pi a naught. This is equal to what? 2 pi a naught. This is equal to integral from negative pi to pi. Then you have f of x dx. So you're looking for a naught. So you divide by 2 pi, and here we divide by 2 pi. So the Fourier coefficient, the first Fourier coefficient we call the fundamental. Fundamental, in case of wave we call it fundamental frequency. This is given as 1 over 2 pi from negative pi to pi. Then we have our function f(x) dx. So this is our general formula that will be using to find the A0 as the Fourier coefficient A0. So we'll be using this throughout the first subtopic. We'll be adjusting these values later on and advance this because this is defining. This is only defined from negative pi less than or equal to x less than or equal to pi. That's how we define this one. So that's the first Fourier coefficient, right? Did you find it helpful? In case you have any questions or you didn't understand any point, please welcome to ask in the comment section. So then let me take you into the derivation while you're meditating about that formula. Derivation of the second Fourier coefficient. Second Fourier coefficient, and this second Fourier coefficient second, okay, so it's a derivations of Fourier coefficient A n. Okay, A n. So we want to find the general formula for A n. So the first state we have to recall the general formula of Fourier series. So the general formula of Fourier series is f of x is equal to A0 plus sigma notation n is equal to 1 to infinity. Then here we have an cosine of nx plus what? Sigma notation n is equal to 1 infinity bn sine of nx. So suppose that this is equation 1. So before, okay, when we have been deriving the general formula of A0, we multiply the first or the Fourier series with integral of dx from negative pi to pi. So remember, there's a close relationship between this coefficient, the second coefficient of Fourier series, which is an, and the cosine function, right? So you say that the second step of derivation, say that multiply equation 1, or multiply equation 1 by what? By integral from negative pi to pi of what? Cos of nx dx to both sides. So let us start on the left hand side. So we have integral from negative pi to pi. Then we have f of x, which we found there. Then cosine of nx dx. This is equal to what? This is equal to integral from negative pi to pi. Then you have A0 cosine of nx dx plus sigma notation. N is equal to 1 to infinity. And then you say integral from negative pi to pi. And then you have what? We have an. Then you have cosine of nx. Okay, then we have again cosine of nx. Then you have dx plus sigma notation from n is equal to 1 to infinity. Then you have bn. Then you multiply with integral from negative pi to pi. Okay, then we have what? We have cosine of nx, which is multiplicand, times sine of nx dx. Okay, so from there again we find cos square we find that we have cos square nx. And then here we have cos nx and sin nx. So if we keep on simplifying, we have nothing to do on the left hand side because we don't know the function yet, f of x. So cosine of nx in dx. This is equal to it. So for the right hand side, we have negative pi to pi. Then we have what? Cos of nx dx. Cos of nx dx. Then we say that plus what? Plus n is equal to 1 to infinity. Then we have integral from negative pi to pi. Then we have what? We have cos square of nx dx. Okay? And then we say that plus what? Plus sigma notation. N is equal to 1 to infinity. Then we have what? Dn. Integral from negative pi to pi. Then we have what? We have sine of nx cos of nx dx. Okay. So, if this is the case, then we have to refer also some orthogonal function. Okay? Some orthogonal functions. We have to refer some orthogonal function and use them effectively. Okay? So these are just, you can take time to prove them because I will teach you soon about what you get if you integrate cosine of nxe dxe, or if you integrate negative cosine of nx dxe. So soon I will teach you. So stay focused, stay tuned. Good things are coming about the higher engineering and scientific mathematics. So it means that, suppose that this is equation 2. If you examine this equation 2, we find that we have firstly, we say, if you're integrating from negative pi to pi, cosine of nx dx, this is orthogonality function. So this is the steady state. Is it? Yes, steady state. Steady state means about orthogonal function. Even if you forget about integrals of orthogonal function, but you have to remember that these are constant. Whenever integrating cosine of nx dx from negative pi to pi, you get 0. But also, take your time to prove it. If you integrate from negative pi to pi of cos square of nx dx, then you get the answer is equal to 0. Get the answer is equal to 0? No. Not 0. This we get to 1. Get pi. Excuse me. Get pi. So here you get pi. If you integrate this, because you know that we told you about how we can integrate cos square nx or cos square x dx. So this is just the upper interval, our upper limit and lower limit. So you just substitute after integrating. For example, if you know what you get when you integrate cos square nx dx, because you know that you have to remember about 20 double angle of cosine, right? So cosine of 2xe or cosine of 2nxe is equal to what? So it's equal to what? Cos square nxe minus sine square nxe. So you can simplify and hence you'll find when you integrate, you'll get the response is equal to pi. Again, we have another constant integral trigonometrical function. It means if you integrate from negative pi to pi, then here we have cosine of nxe, sine of nxe, dx. This also is equal to 0. Alright? So you see that in case these are constant everywhere in the world, at any time, whether you are learning this stuff during the night, during the morning, they still have the same values. That's the goodness of mathematics. So we can call this one as the equation 3. We can call this one as equation 4. We can call this one as equation 5. So we can go for the first step. The first step, we can say that substitute equation 3, equation 2, equation 4, and the equation 5 into equation 2 that we have here. So the equation 2 on left hand side, we have never done anything else. We have integral from negative pi to pi of f of x. Then you have cosine of nx dx. This is equal to what? So you have a naught integral of cosine of nx dx from negative pi to pi is going to be equal to 0 plus sometimes of undergraduate students summation present and future generations. So summation from n is equal to 1 session to infinity. Then you have what? 8n. The integral of cosine square nx dx is equal to what? To pi. And then plus what? Plus summation from n is equal to 1 to infinity. Then you have bn, we multiply with 0. So the next step we simplify. This is 0, this is 0, this is constant. So we have pi an. And summations of 1 from n is equal to 1 to n is equal to infinity, which is equal to 1. Okay, so ladies and gentlemen, I believe that you're enjoying the beauty of higher engineering and scientific mathematics for undergraduate students, right? Remember to share these contents with your colleagues, with your classmates, with your college mates, with other engineering students in other institutions, in other countries. Share with them the beauty of this stuff. So on the left hand side, we have integral from negative pi to pi. Then we have the function f of x. Then we have cosine of nx dx. This is equal to 0 plus what? So an times pi. So this will be pi a subscript of n. And then here we have summation from n is equal to 1 to infinity of 1, which is equal to 1. Then plus what? Then plus 0. So simply, we have negative pi from negative pi to pi, f of x, cos of nx dx. This is equal to what? This is equal to pi times what? An. So pi, this side we divide by pi. So simply this and this cancel. We can rewrite in this way. An is equal to 1 over pi, integral from negative pi to pi. Then we have our function f of x. We have cosine of nx dx. So this is the general formula of second Fourier coefficient. That is 1 over pi. So a subscript of n is equal to 1 over pi from negative pi to pi, f of x, cosine of nx dx. But this is valid for negative pi less than x less than or equal to pi. So this is general formula of the second Fourier coefficient. Wonderful. So that is the second general formula of the second Fourier coefficient. So this is cosine function. Okay. So then now, with the same procedures that we've been following, you can try. You can pause the video and then try yourself to derive the formula of the said Fourier coefficient, which is Bn. But you have just to multiply with integral from negative pi to pi of what is sine of nx dx. Wonderful. So you can pause the video, you can try yourself, and then so you can keep on watching. You press the buttons of play, and then you see the corrections of what you expected it to do. Because we like students who like to try, and that's how you master mathematics. So mathematics or high engineering mathematics and higher scientific mathematics demands students to be hands-on. So I'll be teaching you how you can be hands-on. It means that how you can deal with this problem. Okay, so then the next stage now, we say that derivation is the last derivation for those who don't like about derivation, but I'm very sorry, it's not an option for us to learn derivation of Fourier coefficient. It's not an option for us to learn about this derivation. Derivations of Fourier coefficient Bn. So let us derive the formula. So derivation of the formula of Fourier coefficient Bn. Wonderful. Okay, so we have to follow some steps, almost the 4 steps like what we did there. So the first step, we say that we have to recall Fourier series. You have to recall the general formula the formula of Fourier series. So general formula of Fourier series is f of x. This is equal to a naught plus what? Plus sigma notation from n is equal to 1 to infinity. Then you have an, you have cos of nx, and then plus what? Summation n is equal to 1 to infinity bn sine of nx. Suppose that this is equation 1. So we go for the second step. Second step, ladies and gentlemen, we have to multiply equation 1 by the integral from the same interval from negative pi to pi sine of n x dx to both sides, left hand side of what? Of equation 1 above. So to multiply it, we have integral from negative pi to pi, and then we have what? We have f of x, then we have what? Sine of nx dx. This is equal to what? Integral from negative pi to pi. Then we have what? We have a naught sine of nx dx, then plus sigma from n is equal to 1 to infinity. Then we have integral from negative pi to pi, an, then cosine of nx, sine of nx, then dx, plus sigma notation from n is equal to 1 to infinity. Integral from negative pi to pi, bn, then sort. So remember that these constant functions, because now I'm going to introduce to you other constant integral functions that once you face them in your process of solving problems, you have to know that the answer is 0. Should not bother yourself. So here we have sine of nx then sine of nx dx. Right? So if we keep on simplifying to get equation 2 from negative, integrate from negative pi to pi, f of x sine of nx dx, this is equal to what? This is equal to integral from negative pi to pi, a naught sine of nx dx plus integral from negative pi to pi. Then we say that I will have sigma notation first. So we have sigma notation from n is equal to 1 to infinity. Then we have it an integral from negative pi to pi. And then we have what? Sine of nx times cos of nx dx plus sigma notation from n is equal to 1 to infinity b of n integral from negative pi to pi. Then here we have sine square of nx dx. So this one will be equation 2. So once we have equation 2, then we can simplify, or we can, yes, we can simplify. So you go for the third step. The third step, we say that we have to deal with what is orthogonal function. So when we deal with this orthogonal function, first of all, we have to know that when we integrate negative pi to pi, sine of nx dx, the answer is equal to 0. Keep that in your mind. Again, we say that when also we are integrating, this is just a repetition because we've discussed it, but when we are integrating negative pi to pi, sine of nx cos of nx dx, the answer is equal to 0. The good news also, when we integrate negative from negative pi to pi, sine square of nx dx, the answer is equal to pi. So this is equation 3. This is equation 4. This is equation 5. So the next step, we have to substitute equation 3, equation 4, equation 5 into the general equation, which is equation 2, and then see what will happen. That will be the first step. About to end this session. First step. Okay? So first step, we say that substitute question 1, not question 1, question 3, question 4, and then question 5 into question 2. So to substitute, we have integral from negative pi to pi, then f of x dx now. There you have sine of nx dx. This is equal to it. So as I say that, this will be a naught times 0 plus what? Here also we have sigma notation from n is equal to 1 to infinity. An times 0, then plus what? Sigma notation from n is equal to 1 to infinity, bn times 5. So left hand side we have integral from negative pi to pi, f of x, and then we have what? Sine of nx dx. This is equal to what? Is equal to 0 plus pi bn. So you have divide by pi to both sides. So on left hand side you have 1 over pi, integral from negative pi to pi. Then we have a product of the function and sine of nx dx. This is equal to what? Bn. Wonderful. Wonderful, wonderful. I believe that you are enjoying the beauty. If you feel from your heart that you want to offer your freewheeling thanksgiving in order to support the running cost, don't hesitate yourself. Send your seed offering. So the telephone number 0759 745331. Okay, so the general formula now of the 30 Fourier coefficient Bn that you are going to deal with is 1 over pi from negative pi to pi. Then you have f of x, then you have sine of mx dx. So ladies and gentlemen, remember this formula because we are going to use it in order to solve problems, mathematical problems. So how many Fourier coefficients do you have right now? 3. So let me just give you the summary. Let me give you the summary of Fourier coefficient. Fourier coefficients. Fourier coefficients. The general formula of the first Fourier coefficient A0 is 1, for this case, for this subtopic, is 1 over 2 pi. The good news is we'll be deriving or reducing some other or Fourier function, Fourier coefficient in other aspects or in other branches, subtopics of Fourier series by just using these fundamental formulas. So then it is 1 over 2 pi, and we have what f of x dx, right? So this is in case you have variable x. If you have another variable such as maybe it is t theta, so you have 1 over 2 pi, so integral from negative pi to pi, and then you have what? F of theta, d theta. So you should not get confused. Then the second Fourier coefficient, we say that we can evaluate it by using this formula 1 over pi, from negative pi to pi. We have a given function, a given periodic function, then you have cosine of mx dx. If it will be given another independent variable rather than x, then you just replace x with that given what independent variable. So Bn is equal to 1 over t over pi, integral from negative pi to pi, then you have f of x, then you have what? Sine of nx dx. So these are the formulas that you have to remember. Before I end this session, let me teach you about about odd and even function. Odd and even trigonometrical function. We have a subtopic that we'll be dealing with is odd and even. Sometimes in some of the questions, they'll ask you that find the odd Fourier series of these functions, or find the even Fourier series of these functions. So if you'll be asked to find odd or even, that's another story. We are going to deal with that. But I want to give you the overview of even and the odd periodic function, because we are going to use this concept in the next lecture, which is lecture 3, lecture 4, and even in other further lectures. So even and the odd periodic function. So remember that in Fourier series, about the Fourier series, we say that is infinite series of 40 trigonometrical functions. And these trigonometrical functions are two, sine and what? And cosine. So we say that, let me just remind you, even function, okay, an even function, we say that if f of x obeys the condition of what? F of negative x is equal to f of x. So we say that then f of x is even function. So we have trigonometrical even functions, which is cosine, the trigonometrical even function, which is cosine, and also we have as a polynomial even function. Okay, so example of even function, we say that if you are looking cos, for example, of negative 45 degree, you can use your scientific calculator to prove the answer is equal to cos of 40 or 45 degree. If you are looking for cosine of negative 120 degree, this is equal to cosine of positive 120 degree. So just use your scientific calculator to prove it, and you'll find it is true. So for that case, whenever we find that we have cos of negative x, generally now, this is equal to cos of x, positive x. Right? Whenever we find that in Fourier series of cos of negative mx, this is equal to cos of positive nx. So you have to remember this, because we are going to use this concept often. That is about 30 even trigonometrical function. Okay? What do you think about all the trigonometrical functions? Because I have to clarify this concept. I have to clarify this concept. So when you say that now we're dealing with body function or the FCT, it means that we say if a periodic function if fx is body function, then f of x, then f negative x is equal to negative f of x. That is. So this is the condition for any function to be what? Body function. And this is the condition for any function to be what? To be even function. F of negative x should be equal to f of positive x. For any function, f of negative x should be equal to negative f of x. Right? A good example of body function, body trigonometrical function, is sine. If you are looking sine of negative 45, you can use your scientific calculator. This is equal to negative sine of 45. What does it mean? It means that you can find sine of positive 45 degree, and then once you multiply with negative, is equal to sine of negative 45 degree. Right? So because remember that sine of this one is negative under root of 2 over 2. While this one will be negative what? Under root of 2 over 2. So you see the equivalence. Then you have sine of, for instance, you can also find even sine of negative 57 degree. Sine of negative 57 degree, this is equal to negative sine of positive 57 degree. General. Sine, whenever we find that we have sine of negative x, this is equal to negative. So negative will get out of the angle, because remember this is angle and this is the sine function. Whenever in Fourier series we'll find sine of nx, for instance, this is equal to negative sine of nx. So remember this for the rest of your life in Fourier series, because you need it. So in the next lectures, I can remind you quickly, but don't get surprised when we replace sine of negative nx with negative sine nx. So it should not be separate, because I have told you already about odd and even periodic function. Not only the trigonometrical functions are, however, that we'll be finding this concept, or in Fourier we have to know about odd and the even trigonometrical function. It's not common for the polynomial function, but for example that f of x is equal to x squared. This is the even function. right? And then if you have f of x is equal to x cubic, this is only function. So this is only, this is given. And you can see it. Because if you introduce negative x squared is positive x squared. If you have negative x cubic, then it will be negative x cubic. If you cube negative x, then you get negative x cubed. So we have also some other polynomial function, but we are much focused on this trigonometrical function. Okay? Okay, so I believe that you've been enjoying this session, which is lecture 2 of Fourier series. And let me just give you the homework 2. Okay? Homework 2. Okay? The homework 2 are basically, I just want you to learn and be competent in derivation. Make sure to do this homework and submit in the comment section your report, right? So we said that use the formula, the general formula of Fourier series. Use the general formula of Fourier series to derive the formula of Fourier coefficient. Fourier coefficients A0, AN, and B. I know that some students will say that the homework is just a repetition of the entire lecture 2. Okay, fine. You could think that's the repetitions of the entire lecture 2. But this homework will make you to be understand and go through step to step. So the way that I ask you that to do this homework, you have to pause the video, and then you derive A0 on any draft, on any piece of paper, and then you check the solutions, whether you missed it somewhere, then you correct it yourself. Because this is an active learning program. Again, next thing you have to, because you've been going through how I've been deriving. So you can derive AN on your own. So you pause the video, you derive AN yourself, because you should be yourself. Don't just go around and think that this stuff might get in your mind automatically. No, you have to do a work. And the work that you have to do is you have to practice. So you have to practice deriving a Fourier coefficient of AN and Fourier coefficient of BN. And you have to remember those formulas, because in the next lecture, that is lecture 3, and I would like to take this opportunity to welcome you. We are going to use those formulas of Fourier coefficient and the general formula of Fourier series on solving problems. So the next lecture, we are going to solve only one example, only one problems of Fourier series. We are going to find, I'm going to teach you how you can find A0, the Fourier coefficient A0, the Fourier coefficient AN, the Fourier coefficient BN, right? And then I'll teach you how you can find the general Fourier series of the given problem. So stay tuned. Remember to subscribe, because we are going to have more than 500 videos in this platform. So we ask you to concentrate, to subscribe, and also to click the icons of the bell, and then just choose the options of all. Then will be the first one to get notification once we add a new video in our YouTube channels that called the Online Undergrad POLYINSTIT of Tanzania, in square bracket OLENJOLAIM. So remember that we have so many contents there you have to go through. In case you have any questions about where you can get or you can access some of the materials specifically, according to your curriculum. Please don't hesitate asking your questions in the comment section. Share these contents, like or dislike the contents, and then make everything to be smooth and share with your classmates these contents, because they can cover at any point. They can cover these contents anywhere at any time. So may God bless you abundantly, and I'd like to thank God who have been with me in this lecture 2 of Fourier Series. God has been faithful. He has been with me in the preparations of this session. The way I taught you is a little bit different from how I taught as undergraduate students of the first year at DIT or at Dar es Salaam Institute of Technology for almost 6 years ago. 6 consecutive years I've been teaching this course. So I taught you a little bit in advanced and simplified way and very interesting way. So I invite you in the next lecture. I thank you, and I thank God who have given you opportunity to join me. I invite you in the next lecture, that lecture series, so that I will take you into the next step of practicing the general formulas that I have taught you of Fourier Coeficients and Fourier Series on solving problems. So stay focused, review these contents, watch these videos several times as well as you can. Tell us in the comment section you enjoying these contents from which institution, from which college, or from which university, or from which country, from which region, from which continent, and tell us how did you find, whether you understand what we have been teaching you or you didn't understand. Tell us in the comment sections also, because we like to have a feedback. So may God bless you abundantly and keep you. Don't forget to send your free will in Thanksgiving in case that you feel of any amount that you feel.